Chapter 13, equilibrium. Like I mentioned with chapter 12, we study kinetics first because equilibrium is dependent upon kinetics. As we know something about reaction rates now. So equilibrium is balances the rate of a forward reaction with the reverse reaction. So each one of these, the forward reaction, we learned how to calculate the K for that one, for the rate law in terms of these reactants. But once you start building up enough product, say you start off with nothing but reactants, which is our initial rates approach. Then once you get some of these products, they start running backwards on their own. So this would be the forward reaction, and this would be the reverse reaction. When these two rates are equal, then you have equilibrium. Now, depending on what their rate constants are, if the forward reaction is extremely fast and preferable, then the reverse reaction, you may require a huge amount of product before you start getting enough reverse reaction to balance. So the actual concentrations that balance will be different for every reaction. All right. So it's useful to see equilibrium in actually two ways. One is the macroscopic way. When you get an equilibrium established, then you won't see any change in concentrations of the reactants or products. Once they reach equilibrium, it looks like everything's just static. But on the microscopic level, we know from kinetics that the activity is frantic. It's just, I mean, if you could shrink down to the size of an atom, you would see blinding activity. But from our perspective, it looks like nothing's happening. It's just static. You got this much, this much, this much, this much. It stays that way. So, and this is a graphical representation of the Haber process where you combine nitrogen and hydrogen to make ammonia. And when we first start out, we have a certain amount of nitrogen in the blue line, and we have a certain amount of hydrogen in the green line when we have no ammonia. But as the reaction proceeds, you build up ammonia and you use up hydrogen and nitrogen. And at some point, their concentrations are constant. That's what we see macroscopically. And that's what we use for calculations that we're going to do for equilibrium expressions. Now, you'll notice also that the stoichiometry in this representation is correct for the reaction. If you look at the hydrogens, when you reach equilibrium and you say if the height to the nitrogen line is 1, then the height to the hydrogen line is 3 times that. So the stoichiometry is 1 to 3. Okay. And then if you say nitrogen is 1, then ammonia should be 2. And it's close enough. So we're not saying the stoichiometry doesn't work. In fact, remember in kinetics, you can't use the stoichiometry to derive your rate law. You can't use the coefficients, not the overall reaction. But in equilibrium, the coefficients do enter into the calculation. And I'm going to show you that in just a minute. All right, this is just another representation showing the forward rate slows down as you use up these reactants. And then as you build up products, that reaction rate increases. and they eventually meet. That's where you have equilibrium. All right. Before we get to the expression of the equilibrium, we call it the law of mass action. We'll get to that in just a minute. Look at this particular reaction and say, what's going to happen if this reaction is at equilibrium? What if you add water to this reaction? You increase the concentration of water vapor, and it's reacting with carbon monoxide to produce hydrogen gas and carbon dioxide. If you increase the amount of water, then what do you have? Well, on the atomic level, you've increased the probability of water molecules countering other carbon monoxide molecules. So you increase the probability of more reaction. So you start to increase the rate of reaction if you increase the amount of water. Let me just draw it. Carbon dioxide, and say we are at equilibrium. These are all gases, so I'm not going to put the G in there. So if we're at equilibrium, forward and reverse rate are the same, and it looks like no changes. But if we increase this concentration, now the kinetic molecular theory says that you're going to have more impacts between this one and what's left of that one, which means you're going to increase the reaction rate. So the rate goes up here until you produce enough of this. So now the rate on the reverse matches it. So as far as the concentration goes, what do you see externally? Well, initially you added more water, so that concentration goes up. But as you reach equilibrium again, that concentration drops. But it doesn't drop all the way to its original level, right? It just drops to where the reaction rate is now balanced by the reverse. So you've used up some of that. That means this concentration goes down. And this one effectively, even though you increased a lot, it increases a little bit at the new equilibrium. And what do you get over here? You've increased that amount, you've increased that amount. So what that says is, if you increase the concentration of one of these reactants, you shift the reaction equilibrium to the product side. Okay. Now let's see, what if, let's see on the next one, what if we add more hydrogen? You should be able to predict that one. We're starting at equilibrium now. So if we increase this one, then you're going to get more impacts with what the carbon dioxide is on this side. That means you shift the reaction this direction to the left until you get the balance again. All right. And that's all based upon kinetic molecular theory. Now, for the law of mass action. I'm not going to show the slide yet because it may not agree with me. I like to use the terminology where we have this reactant with its coefficient and this reactant with its coefficient is now in equilibrium with that one and that one. So the small letters are the coefficients. Once you reach equilibrium, we can write an expression at a given temperature, as long as the temperature is constant. Then you can say we have an equilibrium constant that we can write in terms of these concentrations. At equilibrium, if we know the concentration of C and D, all we have to do is raise them to their coefficient power. And then in the denominator, we do the same thing with the reactants. Right? So that's a general expression for the equilibrium calculation, for the equilibrium constant at a temperature. If you change temperature, this will change.
So in organic, it has the EQ below the C. So is it different from this, or is it just?
EQ below the C.
Yeah, like over the expression.
Over here?
Yeah,
Oh,
it's just written out differently.
yeah.
Okay.
I'm assuming that we're at equilibrium. We're at equilibrium. So any expression of concentration assumes that all of them are equilibrium concentrations. Yeah. Yeah, that's Carty's little tick, I guess.
I just noticed it looked a lot different.
Yeah, well, this is the general format. And the investigations that led to this law were done by Peter Wege and his brother-in-law, Cato Goldberg. So they're Norwegians. So it seems like during the 19th century, activities in chemistry and physics were pretty substantial in Scandinavia, right? Denmark, Sweden, Norway had a lot of prominent scientists come out of those countries. But they did their work before any substantial contributions were made to the understanding of kinetics. Kinetics came after this. But now that we know kinetics, a little more about kinetics, that's a better approach to do it first and then go this way. But historically, the equilibrium investigations came first. Okay, they were interested in quantifying chemical reactions and trying to describe them mathematically. And this is what they came up with. They had different words for it back then. They called the study of reaction rates chemical dynamics, and equilibrium is chemical statics. And that just means that what you observe looks like it's not moving. Concentrations are fixed. And reaction rates, of course, we know are dynamic. Dynamic always means motion. Actually, it comes from the Greek root that we use for dynamo. You know what a dynamo is? It's an electrical generator, right? And dynamite, right? It's dyno. Dyno, I think, means power. Anyway, the expression here, whenever you see a square bracket, you can assume that the concentration is molarity. Okay. But this expression can also be, if we use different units of measure here, say these are all gases, right? If these are all gases, then their relative concentrations could also be expressed as partial pressures. Okay. So we could say the partial pressure of C times the partial pressure of D, and this is to the C power and the D power, divided by the partial pressure of A to the little a power and the partial pressure of B to the B power. That would be another expression of K, but it wouldn't be the same as this one because you're using different units of measure. Usually if we do this, we do it in the atmospheres. So this would be like a K sub P to designate pressure. Now these two are related, and we can interchange them with the proper formula, and that comes later. We're going to get to it. Okay. So there, I did correct that slide, so it looks like the one I want. Notice another thing, that whenever you look up K values in a reference manual, they will not have units with them. And they won't have units because keeping track of the units when you have so many reactants and so many products at different powers, it's a mess. So we just have to be really careful when we derive the K and we use the K value for an expression that we correctly set up the expression. And then the units will come out in concentrations. Let's see. There's another rule here that I wanted to get to. Maybe it's in there and I just missed it. Okay. These are all gases. So during the process of chemical reaction, their concentrations can change. If we had instead solutions of each one of these, say they're all aqueous, right? During the chemical reaction, their concentrations can change also, right? Absolute amounts in a volume gives you a concentration. But if any one of these is in a phase that does not change concentration, like a solid will not change concentration. It'll just be used up, and part of it will be used up, depending on the conditions, maybe all of it will be used up. But its concentration doesn't change. I mean, it's just a solid. The other possibility is a pure liquid. Right? So if you have phases that are solid or liquid, then they are not part of the expression. If this is the case, say if this is a solid, liquid, and those are aqueous, then these two terms are gone. And the only expression for this K with these phases is just that term right there. Okay. That's one of the things you have to be careful about when you write one of these expressions. Since we don't have units, then you can't police yourself with units. You have to police yourself with the rules. All right. So, remember Hess's law, where you can combine equations and you can calculate the theoretical enthalpy for a reaction. Well, we can combine equations and we can propose a composite equilibrium constant for a combination of equations. So in order to do that, similar rules apply. You have to, if you've got a target equation that you're looking for and you add up several equations, we have to know how to combine them so that you end up with the target. And what do you do with the K values? So you have to change one of these equations by multiplying it by a constant, or you have to flip it in order to get the Hess law to work. Then what does that do to the K's? Because if you don't do the K's correctly with those changes, then your answer is going to be wrong. So these are the rules. If you reverse the equation, right? Let's put it back. Say these are all some type of concentration that does change. So we can rebuild it like this, like that, and that's a valid expression. So what if we flip that equation around? Say we have to reverse the equation in order to make it fit with our needs. That means now the denominator's on top and the numerator's on the bottom if you reverse the equation, right? So that means the new K is equal to the original K inverse, right? Or some people prefer this. Same thing. You just take the inverse of it because we flipped it. Okay. That's the easy one. What do you do if you have to multiply your equation by a constant? Say we have to multiply it by some factor n. Right? So that changes each one of these by a factor of n, correct? So that's n, that's n, that's n, and that's n. Okay, what does that do to the k? Well, remember your math laws. If all these are each multiplied by each other or divided into each other, and you have the same power factor times each one, then you can factor that in out. We can take that in like this and do that. It's the same thing. So what does that do to your k? Your new k now is equal to the k e cubed to the n power. So if you have to multiply a factor times your equation to get it ready to add to the others, then that n, then the KEQ that you did have now is to the n power. All righty. K is a constant as long as the temperature doesn't change. If the temperature changes, then the K will change. Now, there's a concept. This is the equilibrium constant. And for any given temperature, it is constant. No matter what you do to the concentrations, once equilibrium is established, then those new equilibrium concentrations go into the expression, and they will always give you that value. Okay? But if we do like we did on a couple of slides before, where we add something here or we add something there, and we cause the reaction to shift to a new equilibrium position, the equilibrium position can vary depending on your, whether you start with some here or start with some there or start with both of them, or you're at equilibrium and you mess with it, right? You're going to end up with a new position that is different concentrations than you had before. And different concentrations in this expression will always give you that one. So the equilibrium position is variable. But the equilibrium constant is just that. It's constant. All right. Now, when you are looking at K values, some of them have subscripts that have special meaning. This would be like a generic. This KEQ could be anything. But we have special ones like KW. KW is reserved for water. And we'll talk about that in chapter 14 and 15, how water can dissociate into hydrogen and hydroxyl, and you can write an expression for it. The K for that is KW. I'm not going to hammer that one right now. If you have an acid that undergoes dissociation, and we'll talk about that one in 14 and 15, then that's what Ka means. It's an acid dissociation constant. You can have a solubility product, and we'll get to that in chapter what? 16. We'll talk about solubility products. That's what that one means. And then in 17, I think this subscript is a formation constant for a polyatomic, not polyatomic, complex ion. Actually, we get that in 16 also. Excuse me. Both of these we'll look at in 16. So these all have different meanings. Oh, and if we have a KP, That's where we use the partial pressures. Okay. Once you learn how to work these equilibrium problems, don't forget, because they're going to come back when we study acids and bases. They're going to come back when we study solubility. They're going to come back when we study complex ions. Right. Once you learn this skill, hang on to it. We're just going to modify it a little bit for each case. All right. So this would be the Haber-Bosch process in terms of two ways. Either the KP, where we have partial pressures, or the KEQ, where we have molarity, expressions of molarity. Right? Either one of those calculations is valid, but they don't produce the same K. But those Ks are related. And that'll come in a slide or two. So the equilibrium pressures, if we measure the equilibrium pressures of these gases, and they turn out to be those values, then we can plug those into that expression there, right? Don't forget the powers. When you calculate your Ks, don't forget the powers because they're essential. And we get a value of 3.9 times 10 to the fourth for the K in terms of partial pressures. Now, if you know the KEQ in terms of molarity, then you can calculate the K in terms of partial pressures using this expression. So the K in terms of partial pressure is equal to the KEQ times our gas constant times temperature, and then change in N. And in this case, N means moles. So what do we mean by moles? All right, let me make some room here. Delta N is a change in moles of gas for the reaction. So if we write the Haber-Bosch process again, we have this gas, we have this gas, and it's in equilibrium with this gas, ammonia. Okay. Deltas, most of the time, mean final minus initial. So delta N would be the final number of moles minus the initial number of moles of gas. So in this case, the final number of moles is 2, right? What's the initial number of moles? 3 plus 1, 4. So delta N is minus 2. Okay, that's what would go right up here, minus 2. Temperature would be in Kelvin. And since we're working with gas pressure atmospheres, this R would be 0.082. Thank you. It's right there. Slide it.
Yeah.
8206 liter atmospheres per mole K. So then you'd have that one times the temperature and this whole expression to, in this case, the minus 2 power. And then whatever the KEQ is times that expression gives you the KP. So you can interconvert them. All right. Oh, here's an example. So if we want to find out what the K is, we found out what the KP was in a previous slide, 3.9 times 10 to the fourth. That goes in here. And then this is our unknown. This is a constant. The temperature, we have to be given the temperature. So at 35 degrees C, that's 35 plus 273 is 308. And then 2 minus 4 is minus 2. If we do that calculation, and then solve for this value, we get 2.5 times 10 to the 7th is the KEQ in terms of molarity. Okay. I mean, we skipped a few steps when we went from, my cursor's not big enough. When we went from the next to the last one to the last one. We did some fancy footwork there. We took that, the product of the R value and the temperature, we took that to the -2 power. And then we divided that into 3.9 times 10 to the 4th to give you the K. Right? Okay. I'll leave that one up there for a few minutes. We won't need it again. All right. So we've used these prefixes a lot in the first semester and this semester. Homo versus hetero. Homo means the same, hetero means not the same or other. So if we're talking about equilibrium and we say the equilibrium is homogeneous, that means all of the reactants are in the same phase. For the Haber-Bosch process, they're all gases. For that dissociation of hydrocyanic acid, they're all aqueous. Okay. That's a homogeneous equilibrium. So obviously heterogeneous means you've got different phases. So the decomposition of potassium chlorate gives you potassium chloride. Those two are solid, but they produce oxygen gas. So this equilibrium, in fact, what would be the KEQ calculation for that first equation? That's it. Because the other two are solids. And this is a product, so it's in the numerator. That's it. That's the whole expression for KEQ for that equation. If we're decomposing water into hydrogen gas and oxygen gas, then its KEQ would just be the gases, right? Hydrogen gas to the second power times oxygen gas to the first power. That's it. Pure liquid water doesn't go. You don't use it. All right. All right, there's the rule I gave you earlier. That was stream of consciousness. So we can qualitatively assess the extent of the expected extent of a reaction based upon its K value. Right? Because if the K is equal to products divided by reactants, then if this value, the calculation of this value with all of its terms is equal to this value with all of its terms, then K is going to be 1. Now that doesn't mean that you have exactly the same concentrations of these that you do those over there, because you've got all the powers mixed in. But if it's in the neighborhood of 1, the reaction you can assume is relatively balanced between production of products and what's left over, the reactants. But if this value is large, what does that say? That says this reaction essentially goes to completion. It produces products and there are almost no reactants left behind, because this is huge and that's really small. But if the value is really, really small, as written, that means this is large and this is small. So the reaction itself doesn't go very far. It doesn't make much in terms of products. Now, what would happen if we just flip the reaction? Right? If K is large and we flip the reaction, now it favors reactants. They were the products, now they're the reactants, and K is going to be small now, right? Because you invert it. And vice versa for the other one. So those are the qualitative assessments we can make from the K value without doing any calculations. That just gives us a overall picture and understanding of how the equilibrium is set up and the character of this reaction in terms of its equilibrium. All right. Let's see. So I'm not going to waste your time here. We already talked about that. All right. What do we do if the reaction is not in equilibrium? Say we set it up with a huge amount of reactants and a small amount of product, right? So we're assuming that the reaction is not at equilibrium, but we want to know which way it's going to go, right? With those concentrations, is it going to go that way or is it going to go this way? That's important to know when we start to do calculations to find out what the equilibrium position is for the reaction. So we're going to, if we know that the K is equal to C and D, like this, let me just go through the steps. We know that the K is this expression, okay? Then these are equilibrium concentrations. But if they're not equilibrium concentrations, then we can calculate a value called the Q. And in that case, I use parentheses to distinguish from equilibrium concentrations. Right? We use the same calculation, but now we're using non-equilibrium concentrations. That gives us a Q value. Oops. A and B. There we go. All right. So if we calculate this value and we know what the KEQ is for that reaction at this given temperature, and we calculate this value for what we have introduced into the reaction container, then we can compare these two values, the calculated value to the theoretical K value for that temperature. The easy one is, if they're exactly equal, you're already at equilibrium, right? You're already there. What if Q is greater than K? What does that mean? If Q is greater than K, that means you've got too much of that and not enough of that. Right? It's large. It's too large. You got too much product. That means the shift is toward reactants. Okay? Or to the left as written. I'll caution you, when we say left and right, if you're not referencing a balanced equation, when you say left and right means nothing. Because I may decide if you say left, I may write the reaction backwards. And then it'll be the opposite of what you expect. So whenever you say left and right, you have to reference a balanced equation. Right? Okay, that's why I said toward reactants. That way there's no mistake. Then obviously if Q is less than K, that means this is too big, that's too small. So it's going to shift toward products. Okay. Based upon this expression derived from this equation. Okay. Good, okay. I thought I saw a frown. All right, and that's the way that the equation, the reaction must change its position in that direction in order to reach equilibrium. All right. So let's take this example. What are we doing on time? Okay. So this expression where you have iron 3 plus ion reacting with the thiocyanate ion. Notice that the charge is balanced, right? We've got 1 minus and a 3 plus on the left side, and then we have a 2 plus on the right side. So those charges balance, but how do you get those two together? Well, the iron has to be paired with a counter anion, and the thiocyanate has to be paired with a counter cation before you put them together. Then when you put them together, the ions that we don't see there are spectators. So we just leave them out. They just get in the way. All right. So for this first trial and that reaction, we have, I'm going to write it first because I think we're going to use this same equation several times. That's aqueous. So we know that one's going to change. And this is thiocyanate ion. And it yields in equilibrium this complex ion. That's CN with a 2 plus. This is aqueous. Right. So when we get to chapter 16, we'll talk a little bit more about that. And actually, you'll be using this reaction in not today's lab, but the next lab we do, the Le principle. Because this is a brick red compound. It's obvious when you put these two together, you get that, and it's just boom. Like, there's no mistaking it. So in this trial, we're starting off with 6 molar, like 6 molar iron 3 plus and 10 molar thiocyanate at a given temperature, and at equilibrium, we measure the concentration of that one at 4 molar. I'm gonna put it down here for a reason. That's after the reaction. Right? When we first put them together, how much of that is there? 0. Right. Before we put them together, there's nothing. So this is the initial conditions. That's the starting condition. The nice thing about this is you don't have to calculate the Q. You can't calculate the Q because this would go in the numerator, right? 0 divided by any number is 0. Right. So that doesn't mean anything. But chemically speaking, if this is 0, the reaction can only go one direction. It's got to go that way. Okay. This is at equilibrium. We measured that amount at equilibrium. Okay. So what change happened here? That's this line that I left out. What changed? Well, we had to lose some of this, didn't we? And we had to lose some of that to make this. So the change went from 0 to an increase of 4. Right? So we add these together and we get 4. Okay. What kind of change did we get here? Well, look at the stoichiometry. It's 1 to 1 to 1. So if we got 4 molar there, we had to lose 4 molar here. Correct? 1 to 1. We also had to lose 4 molar here because they're 1 to 1. Now at equilibrium, we should have 2 molar here, and we should have 6 molar here. So now that we know the equilibrium concentrations, we can calculate the KEQ. KEQ is going to be concentration of the I was trying to scratch in my head for the proper name for this. Remember my nomenclature. Thiocyanate iron 3+. That's what it is. Okay, 3+ here, and we have this one here. Right, they're all to the first power. So all we have to do is put the values in. I'm not going to write molar in here because we're not going to keep the units anyway. Six. Right? So what's 4 divided by 12? Well, let's do this. 2 into 4 is 2, right? And 2 divided by 6 is 1/3. That's the KEQ for that reaction as given.
So since we take away 4 from iron and the other one, why wouldn't it be +8 instead of +4?
Oh, because 4 molar goes into this position. This 4 molar goes into that position. So it's 4 molar this and 4 molar that, which means 4 molar together. You're not making 8 molar. I mean, you're using up 8 molar ions total, but you're only using up 4 molar of this one and 4 molar of that one. And when you put them together, this one plus that one yields this one. Okay, it's the stoichiometry of the equation, not the additive effect. All right. So what I've created here on the table, this is called the ICE table. You'll be using that one a lot. Initial, change, equilibrium. That keeps everything straight. All right, so our K is 0.333. Now that we know what K is, as long as we don't change the temperature, we can change the values in here and calculate what the final concentrations should be if we start off with a different amount. Say, in this case, we're going to start off with 10 and 8. Let's see, is that right? 10 iron, yes. 10 here. That goes out, that goes out. This is 10. This is 8. And that's 0 at the beginning. Okay? All right. So what they want to know is what's the concentration over here? What's the equilibrium concentration of this complex ion? All right. Scratch my head for a second. We're going to lose some of this and lose some of that and produce it over here, right? So the stoichiometry says that we're going to lose some of this and we're going to lose exactly the same amount of that. But we're going to end up adding over there that amount. So now we have, at equilibrium, we have 10, I should only have one. 10 minus X and 8 minus X, and this is X. So whenever possible, look at the question. The question asks for the concentration of this species right here. If you can make your unknown value equal to the answer you're looking for, that will save you a step in calculations. So we made this one X, or I made it X, so that when we solve it, when we find X, that's our answer. So now, this is 0.333. So 0.333 equals what? X. Actually, to be consistent. There. And this is 10 minus X. And this is 8. Okay. Go to the next page. I think it works it out for us. All right. So we've got an equation here and one unknown. But notice what we're going to generate here. That times that gives us a quadratic. Quadratics are a headache. Now there's a trick that we can use sometimes, but it's only when this value is very small. Like 10 to the minus 2, 10 to the minus 3, minus 4, minus 5, minus 6. If this is very small, then we can ignore these x's and keep that x in the calculator. But this is too large. We have to keep that. We have to keep those x's. So what we end up with is a quadratic expression, and well, it's there on the slide. So I'm not going to waste our valuable time by going through it. What you do is you know how to expand a quadratic, right? This one times this one is the number part. This one times this one is the x squared. And this one times that one, and this one times that one, add those together. Right? And that's your x factor. So you have an x squared, you have an x factor, and you have a constant. And then you resolve the x factor with this factor. You have to go over here times that. And then you have to get all the quadratic on one side equal to 0. That's what we've done at the bottom there. So that's what we end up with. 0.333x squared minus 6.99x plus 26.64 equals 0. Once you got to that point, then you can use the quadratic equation. Now, sometimes I can remember it and sometimes I can't. So I got it on the back of my calculator. The x squared coefficient is A. The x coefficient is B. And the number, the constant, is C. And that goes into your expression of x equals minus B plus or minus the square root of B squared minus 4AC, all divided by 2A. That gives you two values, right? Because it says plus or minus. So you got two values here. If x is either 15.99 or 5, then you got to decide which one is physically possible. X can't be 15.99 because neither one of these is big enough. Right? If you subtract 15.99 from that, you get a negative value. So it has to be the other one. It has to be 5. So the value of x, or this concentration, is 5 molar. Okay? Now, there are two ways to handle situations where you have to solve an equation with powered unknowns, powered x values. If it's a quadratic, you can go straight to this one. If you can't use the trick I talked about, and we'll do some problems where you can use that. Then the other possibility is the successive approximations. If I go ahead and say, knock that one out and say it's actually 10 times 8, say x divided by 80, then 80 times this is equal to x. I get that value, and I'm pretty sure it's wrong, right? It's not going to be 5. But what I do then is I take that value that I say is x, and I plug it in here and here. Leave that one alone, and do the calculation again. And it gives me an x value. Most of the time, by the first iteration, the first approximation, the first approximation was that one. The second approximation gives you an x value. It's going to be close to the right answer. So the way you find out whether it's right or not is you go back and you plug that X into all these places and say, how close is it to 0.333? Is it within 5%? If it's within 5%, you're good. If it's not, you go back, plug it in here, leave that one alone, calculate it again. And that's the way researchers in chemistry do these types of equations when they have very complex reactions that are going to have lots of powered factors in there. And they're not just going to be quadratic. They're not going to be cubic. They might be quartic or more, 5, 6, 7 power strings. Those are even hard for supercomputers to and I don't even know if they have a formula for those. I know they have one for cubic, and it's a mess. So if we go past quadratic, we'll use approximations. But approximations work. You can set up a computer program that'll do it for you much more efficiently than trying to actually solve the equation for the exact answer. All right. So if we were to go back and do this calculation all over again, set it up like that, then the different values give us a different equilibrium position, but the constant is the same. So we're calculating equilibrium positions when we solve these ice problems. Okay, you always need a balanced equation. That's the first place you start. And actually, before you even get to the balanced equation, if you're given a word problem where you're given the names of your compounds and the names of your reactants and products, then you got to be able to write them in their formula. Otherwise, you're stuck. You can't balance your equation. So that's why in the first semester, I was so insistent upon learning nomenclature. All right. So once you get the balanced equation, you write the equilibrium expression. And then you list the initial concentrations in your ice table. If necessary, calculate the Q. If you're given a value of this, and this, then calculate the Q and determine which way it's going to move. Because that says, if it's going to move this way, then these are going to be pluses, and that's going to be a minus. Okay? But if any one of them is 0, say if you have a value here and this one's 0, but you have something here, then you know it's going to move that way. It's going to move toward the 0. Those are the ones I like because I don't have to calculate Q. All right. Then you set up your expression so that X actually gives you the answer you're looking for, if at all possible. It's not, sometimes it's not possible, but whenever it is, make X the answer that you're looking for. And then check your calculated values to be sure that it jives with your K. All right, here are 3 possibilities. We're not going to go through these. They're different starting points for your equilibrium. And in fact, if we're actually given values there, so you do have to calculate the Q's for these to know which way it's going to move. And if we had time, I'd do one of them, but we don't have time. There are the answers. All right, so if you do them yourself, then you can check yourself against those answers at equilibrium. So if we introduce ammonia into a 1 liter container, 2 moles of it into a 1 liter container, what's our starting concentration of ammonia? 2 divided by 1 is 2 molar, right? It's molarity, 2 molar. So is that equation balanced? No. You have to balance the equation. Then we're told at equilibrium, 1 mole of ammonia remains. So we've used up 1 mole. Calculate the value of K. All right. So if we set up, oh, we didn't set it up. All right. Don't need that anymore. So how many more slides do we have? Do I have time to do this? Yeah. I'll set it up, but I won't go through the whole solution because we don't have time. Well, let's see. Yes. We're decomposing ammonia, right? They're all gases. So we end up with hydrogen and nitrogen gas. So this one's going to be 3, and this one's going to be 1. This one's going to be 2. There you go. Okay. We're starting off with 2 molar ammonia. Initial concentration. Right? And nothing here, nothing here. So we know it's going to go that direction. We're told 1 mole of ammonia remains. So down here, we've got 1 mole still in a 1 liter container. So it's 1 molar. Okay. That means we had to lose 1 molar in the process. So if this is 2, then the single factor would be 0.5. Right? And 0.5, 3 times 0.5 is 1.5. Or you can use your dimensional analysis. Say, if this is 2, then that's 3. And if this is 2, this is 1. Right? Okay, so now we have 1.5 and we have 0.5. We can calculate the K now that we've got those values. We just need to write the expression correctly, right? KEQ equals hydrogen concentration to the 3rd power, nitrogen to the 1st power, divided by ammonia to the 2nd power. There we go. Just plug in the numbers. And you should end up with 1.69. 69. Check yourself and see if that works. All right. We could go in here. Let's see. Does this have? No, this is not worked out. All right. I'm going to let you set this one up. This is, they're both gases, right? Dinitrogen tetroxide is decomposed into 2 nitrogen dioxides, and we're given the K value. The K is very small. Maybe I better set it up. But we got till 11:15. Yes, maybe I better set it up and don't have time to work it out, but I can at least set it up for you. All right, so we got this molecule here in 204 is in equilibrium with 2. Okay. Let's see. 1 mole sample of this in a 10-liter vessel. So 1 divided by 10 is 1/10, right? So initially we have 0.1. How many decimals? 2. Oh, 3 significant figures. There we go. That's what we're starting with. And this is 0. Okay. We want to know the equilibrium concentrations of each one. So we know it's going that way. Right? If we lose some of that, then we're going to show it's going to show up as twice that amount of here because of the stoichiometry. So we've got 0.1 minus X, and this is 2X. So our equilibrium constant is, where is it? 4 times 10 to the minus 4. So this is 4 times 10 to the minus 4 is our equilibrium constant, is equal to NO2 squared over N2 4, the first pattern. So that's 2x squared divided by 0.100 minus x. That's equal to 4 times 10 to the minus 4. This might work out okay. All right, we can use the trick on this one. Since this is very small, then this value is augmented by that x, not very much. I'm going to say that that x is approximately, is so small compared to this value that it doesn't matter, right? Because 10 to the minus 4 means it's not moving this far to the left. That means we're not going to lose a lot of that. So that value is going to be extremely small. So I'm going to go ahead and square this one. 4x squared over 0.100. So we're dropping that x out. So 0.1 times this, right, 4x squared then, 0.1 times that value is what? 10 to the minus 1 times that one would be 10 to the minus 5, correct? Multiply this by a 10th. Okay, so then 4 divided by on both sides times 10 to the minus 5 is equal to x squared, and x is equal to the square root of 1 times 10 to the minus 5. 3.16 times 10 to the minus 3. Okay. Yeah, is that one of them? X. No, that's not either one of them. This is 2x. So 2 times that value would be x. This is 6.32 times 10 to the minus 3 molar. And this is 0.1 minus x. So 3.16. And that's subtracted from 0.1. And I get 9.68 times 10 to the minus 2. So does that agree? Come on. Give me the answers. 0.097, yeah, in standard notation. 0.097. How about the other one? 6.32 times 10 to the minus 3. Yep. So in order to see if that is actually correct, and actually if we say x is 3.16 10 to the minus 3, that is 2 orders of magnitude smaller than 0.1. So we're pretty safe by saying x is insignificant in this calculation. But the only way to be absolutely certain is to take that x value, stick it back in here and here, and calculate it and see how close it comes to that value. It needs to be within 5%. Okay, now we're going to talk about Le Chatelier's principle. We actually started talking about it earlier when we had a balanced reaction in equilibrium and we changed the concentration. We saw what happened to the equilibrium when we changed that concentration. That's the beginning of Le Chatelier's principle. Le Chatelier says that if a system, in our case, a chemical reaction, if it's in equilibrium and you do anything to disturb that equilibrium, the system will react in such a way as to minimize that disturbance. Okay. the change, it will try to reduce the change. There are three ways that we can disturb a reaction. One is concentration. We talked about that one already. So the system will shift away from the added component. Or if you remove a component, the system will shift toward the removed side to try to replace some of it. Concentration is easy to understand. Let's see. Oh, I got a video. Cut the
The
lights.
Choquetet's principle states that if you have a reaction to equilibrium and you apply a stress to that equilibrium, the reaction will shift in a direction in order to relieve the stress.
Here.
We will look at a series of different reaction equilibria. We'll apply a stress to those equilibria and see in which direction they shift. In the reaction between iron plus 3 ion and thiocyanate ion, if we add some iron plus 3 in the form of iron 3 nitrate, and to the iron 3 nitrate add some potassium thiocyanate, the two react to form a reddish orange complex ion. We fill 2 test tubes with the reaction mixture. We're going to keep one test tube as a control so that we can see what happens to the color. To the other tube, we're going to add some 0.1 molar iron nitrate to increase the concentration of the iron. We see that there's an increase in the dark red color. This indicates an increase in the concentration of the complex ion. This also indicates that the reaction has shifted in the forward direction. As you add reactant to an equilibrium, the reaction shifts in the direction to use up the added reactant, in this case, the forward direction. Now we'll add 0.1 molar potassium thiocyanate to the second tube. This increases the concentration of the thiocyanate ion. We see that the reaction mixture turns a darker red color, indicating an increase in the formation of the complex ion. We've added the other reactant, the thiocyanate. The reaction shifts in the forward direction to use up the added reactant. We will now add some 1 molar sodium hydroxide solution. We notice that the red color decreases significantly. This indicates that the reaction equilibrium has shifted in the reverse direction. The hydroxide ion precipitates the iron ion, effectively removing it from the solution. The equilibrium shifts in the reverse direction to try and increase the concentration of the iron. We will now add solid potassium chloride to the solution. We notice the decrease in color, indicating that the reaction has shifted in the reverse direction. The chloride ion forms a complex ion with the iron, effectively tying up the iron concentration. The equilibrium shifts in the reverse direction to try and replace the iron that's been removed. We will now add 0.1 molar silver nitrate to the reaction mixture. We notice the disappearance of the red color, which indicates that the equilibrium has shifted in the reverse direction. We also see the formation of a small amount of white solid. The silver ion reacts with the thiocyanate ion to form slightly soluble silver thiocyanate, which is the white solid. The silver ion removes thiocyanate from solution. The equilibrium shifts in the reverse direction to try and replace the thiocyanate ion that's been removed. We will now add some 0.1 molar mercury 2 nitrate. The mercury plus 2 ion reacts with the thiocyanate ion to form a new complex ion. This effectively reduces the concentration of thiocyanate in the solution. The equilibrium shifts in the reverse direction to try and replace the removed thiocyanate.
That's the next one. The reason I wrote these up here is because this is a common technique when we're trying to demonstrate Le Chatelier's principle. It's easy to add things. You can add iron and shift it that way. You can add thiocyanate and shift it that way and make this red complex ion. But when you're trying to remove and shift it back this way, you have to use what's called a coupled reaction. So if we couple this reaction in that solution, remember all of this is in that solution together. So the hydroxide reacts with the iron 3+ and makes this soluble complex, but it effectively removes the iron 3+ from the reaction, the primary reaction equation. So it causes the shift this way, and you see the red disappear. Or you can do the same thing with chloride ion, and form this complex ion over here. You're removing iron. Or you can add silver, which forms a precipitate with the thiocyanate. Okay. And that effectively removes thiocyanate, and the reaction shifts to the left again. And then the other one I have put up here, he made a complex ion with mercury and thiocyanate. But what you're doing with these coupled reactions is you're affecting the primary reaction in terms of removal of a reactant or product. Okay? All right. Now, let's see what the effective temperature is on an equilibrium situation. So we've looked at concentration. Now we're going to look at temperature. What's the effect of temperature on a reaction? There are two ways to approach this. We know that the K is going to change if you change the temperature. So the chemistry way to look at it would be to see what does the change in temperature, what effect does that have on the equilibrium constant? And then that will cause a shift in the equilibrium. But that takes too much time. It's easier, it's simpler to say if we have an equation that's in equilibrium, like this, what we want to know is this reaction endothermic or exothermic? If it's exothermic, then I put the enthalpy into the equation as a product. So an exothermic will produce a product, will release heat as a product. Now, if we change the temperature, if we increase the temperature, we're effectively adding enthalpy, which shifts back this direction. Or if we decrease the temperature, we're removing that factor and it shifts that direction. This would be decrease temperature. This would be increase temperature. Right? What then if it's an endothermic reaction? Now the enthalpy goes on this side. Right? It absorbs heat in the reaction. Now, if you increase the temperature, you're increasing this factor, and you shift toward the products. Or if you decrease the temperature, now you're shifting back this way. You're removing heat, and you're shifting the reaction that way. Okay? All right. So if you don't know if the reaction is endothermic or exothermic, when you change the temperature, you either have to throw your hands up or you make assumptions. All right, that was temperature. The other factor is pressure. And that's usually in the form of a change in volume. We're using Boyle's law there. All right, so if you change the pressure of a system by changing the volume, right? We don't want to change the pressure by adding reactants or adding, removing reactants or adding products, because we already covered that one up here. So changing the pressure, we're going to do it by changing volume. So if you decrease the volume, you're increasing the pressure. So how will the reaction react to your insult? It depends. It depends on the number of moles of gas on one side versus the number of moles on the other side. So let's use Haber again. Let's say we have nitrogen gas plus hydrogen gas is in equilibrium with ammonia. Okay. Let's see. Yeah, that's right. Notice that on this side, we have 2 moles of gas. On this side, we have 3 plus 1 or 4 moles of gas. When you have a different number of moles on either side of gas, this is gas only. If you got any liquids, any solids in there, it doesn't matter. They don't count. But if you got difference in number of moles of gas, then we can say something about the shift if we change the pressure. If we increase the volume here, the system is going to respond by decreasing the number of moles of gas, which relieves some of the pressure. Remember, if you decrease the number of moles of gas in a container, you're decreasing the pressure. So if we decrease the volume, which increases the pressure, right, both of those together, then the system was going to respond by producing fewer moles of gas. And vice versa. If we increase the volume and decrease the pressure, we're going to shift it back this way. Okay? Now, what if you had a reaction where you have equal number of moles of gas on both sides? Once it reaches equilibrium, if you change the volume, it will have no effect on the reaction, because the reaction's got nowhere to go, right? If it's equal volumes, equal moles on both sides, it can't respond in any way to change that. What if here's another possibility. What if you increase the pressure by adding an inert gas that's not even part of the reaction? It has no effect. None. Because it's not part of the reaction. You're actually, by increasing the pressure, you're not changing the number of impacts of this one or the decomposition of this one in the other direction. You're not changing that when you add an inert gas. You'll have more impacts, but you won't have impacts with reactants. Okay, so adding an inert gas is effectively, for any equation, is the same as if the equation had equal moles on both sides. All right.